Good morning, dear students. Let us move into session 4 of this first module. So in the previous session, we have seen about number representation and how do we represent signed integers using 3 different formats. And we also seen arithmetic operations on this signed integer representations. So today we'll just continue with that with overflow topic and sign extension. And we'll also look into memory addressability and its assignment. So overflow, as we have already seen, is an error condition whenever the result of the addition or subtraction process is outside the representable range of the system. So what I have discussed in the last class was no overflow condition. I've taken some examples and shown you the results also. So for example, in a 4-bit system, we know that the maximum negative number is -8 and the maximum positive number is +8. So if the result of your arithmetic operation is within this range, then there is no overflow. Whenever the result exceeds this range, then that is an error condition. We call it as an arithmetic overflow. Okay. And two important things we can easily observe from those examples, what we solved in the previous session, that overflow cannot occur when two numbers having opposite signs are added, right? Two numbers with opposite signs, when they are adding them, they cannot be an overflow. For example, I'll show here. Suppose I try to add, say, +5 with, say, -7, let us say. And you usually know that the result of this is -2. And -2 is definitely within the range. So whenever two numbers of opposite signs are added, you cannot get an overflow. That's the easy thing to remember. Then second condition is, even if you add the numbers of the same sign, and if the result is within the range, then also there is no overflow, right? So for example, I do +5 added with +2. The result is +7, and +7 is within the range, so there is no overflow, right? So overflow can occur only when, I'm just marking this, you can see there, overflow can occur only when two numbers having the same signs are added and result exceeds the range. It's very important. Result exceeds the range of the numbers either on the positive side or on the negative side. So I'll just show an example. So observe what I'm writing now. So let's say I'm trying to add +4 and +5. And you know that the result of this, of course, on mathematics, on pen and paper, if you do, it will be +9. We also know that. But unfortunately, as we have already seen, +9 cannot be represented with 4 bits. Cannot be represented with 4 bits because maximum positive number is +7. We've already seen that. So this itself is an overflow condition. Okay. So overflow can occur when you add two numbers of the same sign and if the results exceeds the range. Now, how do we know that overflow has occurred? Is there any simple method to know that overflow has occurred? So by observation itself, we can find out that overflow has occurred or not. So one of the easiest method to know about overflow is when the input numbers are of the same sign and the result is of the opposite sign, there is an overflow. Okay, the first condition is if the input numbers are of the same sign and the output result is of the opposite sign, then there's an overflow. That means suppose you are adding two positive numbers, you get a negative number as a result, then that's an overflow. Or vice versa, you add two negative numbers, but you get a positive number, then that is also an overflow. Fine. This is one of the condition. Other condition is you observe the carry into the MSB position and carry out of the MSB position. And anyway, carry out of the MSB position called as end carry is always discarded, as I said, but we'll just observe that. So if there is a carry into the MSB position or carry outside the MSB position exclusively, that means only one of them should occur, then there is an overflow. Okay. So that condition is given here in the last equation. V is, that is overflow. If I have a flag to indicate this overflow, then I can show that V is exclusive or of carry into the nth position and carry into the n-1 position. So we'll just take an example and check that here. So no overflow we have already seen, so let us not discuss that now. So you can see here, let us say I'm trying to add -7 with -2. Okay, so -7 with minus 2 if I'm trying to add. Okay, this one, so minus 7 with minus 2. The result of this is actually minus 9. And from the diagram previous representation, we can easily see the maximum negative number is minus 8 in 2's complement format. So minus 9 cannot be represented. And this is the end carry what I was discussing. End carry is anyway always discarded, so let us not worry. So we look into the remaining 4 bits. So this number is a positive number, you can see, because the MSB is 0. So I'm just writing here, you can easily see. So this means this value is plus 7. So now carefully observe, students. I'm trying to add minus 7 with minus 2. I'm supposed to get minus 9, but I'm getting plus 7. This is what I said when two numbers of the same signs are added. Okay, that is the number of the inputs are negative, the output is positive, so it's an overflow condition. Okay, so there are some other examples which I can just show you here. Your example here. So I'm trying to add minus 6 with minus 7. Okay, minus 6 with minus 7. So minus 6 added with minus 7, we actually expect minus 13. And with 4-bit, please remember, I'm discussing only a 4-bit system. Of course, if you go for a 5-bit system, the numbers are again different. So in any n-bit system, if the result of the computation is outside the representable range, then we say it is an overflow. Okay. So, and this, you can see this is the end carry, which is discarded because I'm looking at 4-bit system. So my result should also be fitting in 4 bits only. So you can see here, these are the two negative numbers, right? Because sign bit is 1, but you see the result, this is a positive number. Whatever may be the value, let us not bother about the value. As soon as you see that inputs are negative and output is positive, you can easily say it's a incorrect result or invalid result. So it's a overflow condition. Similarly, here you see these two are positive numbers because the MSB is 0, the sign bit is 0. Look at the result. The sign bit of the result is 1. It means it's a negative number. So I'm trying to add two positive numbers, but I'm getting a negative result. So this is an overflow. Okay. Similarly, during subtraction also, subtraction is also taken as addition, as we know, with 2's complement method. So during subtraction also, you can easily see that, see, the inputs are positive, the output is negative, so it's an overflow. Okay, so just by solving some few examples, you can easily come to know. Of course, you cannot read this, it's a numerical thing. Please take a pen and paper or your notebook and then try to solve this. That's how it helps you to understand this concept. So one method I have shown you, observing the sign of the input and the sign of the output. If they are different, there is an overflow. Second method I told you is observe the carry into the MSB and carry out of the MSB, right? Both should not be present at the same time. They are mutually exclusive. So again, look at this example. See, there is a carry into the MSB position, right? Carry into the MSB position. Whereas here you can see there is a carry 1 plus 1, this one. Carry out of the MSB position. So I'm just showing the annotation, you can as well see here, right? So it means what? So if they are mutually exclusive, that means they should not occur at the same time. So carry into the MSB is not same as carry out of the MSB. Then also I can say that there is overflow. So please try to solve more examples on this. Anyway, I have given in the notes also, in the MCQs also I have given. So please try to solve and understand this concept. Okay. Now let us move to the next topic, which is sign extension. And just now we have seen how do I represent a 4-bit, a signed number using 4 bits, right? Suppose I want to write, say, plus 4. So plus 4 is 0, 1, 00, where 0, the MSB represents sign. Suppose I do have a system or a computer or a computing device which actually takes everything in 8 bits, let us say. But I have only 4 bits. I have represented using only 4 bits. So what can I do now is I can represent the same number without changing its value using 8 bits also, 16 bits also, 32 bits also. So from the given system, you want to extend it to a higher bit system. Then what you try to do is you just copy this sign bit into the higher position. Suppose this 4-bit system I I want to represent this 4 as a 8-bit number now. So what I'll do is I'll simply extend the sign bit of the original 4 bits into the next higher 4 bits. So this together is a 8-bit number. Of course, the value of this number is also plus 4. I'm not changing the value. I'm just representing that number with a higher bit system. Okay, usually, as we all know, today's computers are all 64-bit systems, right? So when you want to represent numbers using higher number of bits, you just extend the sign, whether it is positive or negative, let us not worry. Just extend the sign bit. The sign remains the same, the value remains the same, only the representation is using higher number of bits. Similarly, -4 also has shown here, you can check. So the schematic also shown for your understanding over here. So you will make copies of the sign bit, that's all. You make k copies of the sign bit depending on how many extra bits you want to represent. Okay, this is called a sign extraction. So now coming to the memory structure. So what's the importance of this now is, till now we have seen how to add numbers, how to represent numbers and all, but all these numbers, data, information, instruction, everything should be stored in memory, right? So in the beginning sessions, I have informed you that memory is like an array of consecutive locations, right? Like I gave the example of your classroom with the number of desks, right? And we have fixed how much can be stored in one location already. That means how many students can sit in one desk, but number of desks will vary, right? So the number of locations in the memory will vary, but how many bits are stored in each location? Binary logic, again, remember this I have explained earlier. So you can store n bits of information in one location, and usually we can take it as 8 bits of information in one location. Okay. So that is fixed. So when I fix the width, this length can be changed depending on what is that I want to store. So earlier I have told you data representations. Your text or ASCII takes less number of bits, whereas your image takes more, your voice and video takes much more. So you need to represent each type of the data using binary bits, and each type of data may require different amount of memory. So you need to know how the memory can be configured. Okay, that's what is this basic introduction to. Of course, we will discuss this again in module 4, but this is a basic introduction towards that. Okay, and this n is called the word length of the memory. Okay, that is this. How much information can be stored in one location is known as n, that is word length. Okay, now data can be 8 bits, data can be 16 bits, data can be of 32 bits, 64 bits, whatever. So we can represent the data using any format, any number of bits. So it means we should be able to store all this data into the memory consecutively. It's very important thing is the information is always stored in the memory in consecutive memory locations, not arbitrarily. Okay. So how do I represent 8-bit data? So let us say I'll just take an example over here. Let us I take a number 25. 25 is a 1-byte number, we call 1-byte number. I think in basic electronics and all, you had already studied all these things, RNC programming, but let me just recall and put you into right perspective. So whereas 1, 2, 3, 4, for example, is a 2-byte number. 1-byte number is a 8-bit number. I'm trying to write here, please observe. And then 2-byte number is a 16-bit number. How do I understand? Whenever I see 2 digits, you take it as 1 byte, right? And whenever I see 4 digits, you take it as 16-bit. Similarly, a big number like say 1, 2, 3, 4, 5, 6, 7, 8, let us say. This is a 32-bit number or a 4-byte number. So you make like this, 2 digits in a group. So this is 1 byte, 1 byte, 1 byte, 1 byte. So totally it is a 4-byte number. 4 byte is same as 32-bit. Right? Please understand this carefully. Okay, so this is the concept of how do we represent your decimal numbers or whatever in terms of binary. Okay. So, and one location will always store only 1 byte. So please remember that one location we are discussing now will store only 1 byte number. Okay. So Here I have given an example of a signed integer, how it is stored. For example, a 32-bit number with, again, whatever may be the size of the number, MSB always represents the sign. Okay. If it is a signed number. If it is an unsigned number, as I discussed earlier, sign bit is not considered. If it is signed number, MSB 0 is positive, MSB equal to 1 is negative. Okay. Similarly, if you are trying to represent the characters like alphanumeric or your name or whatever, each character is represented by 8-bit ASCII, 7-bit ASCII plus 1 parity, that is 8-bit ASCII. ASCII table I have given in the notes, you can please go through that. The standard, this is a standard one, American Standard Code for Information Interchange. So each of this, that is whatever is there on keyboard, your digits, your special characters, your alphabets, uppercase, lowercase, everything has an ASCII value. Okay, suppose A is 41 in hexadecimal or 65 in decimal. B, letter B is 42, something like that. So each of them will be represented as 8 bits. So with 32 bits, I can represent 4 characters now because one character size is 8 bit. Even in C programming, I have studied no size of char, size of int, like that, same way. Okay, this is how you try to understand this. Okay, now I said number of locations in the memory are can be varied based on your need to store. So you want to store an image, you need more memory. You want to just store only text, you don't need much memory, right? So how I decide about number of locations in the memory? Okay, this also cannot be done arbitrarily. Okay, this also I cannot do arbitrarily. I have to check this with respect to what is known as address bus. In the initial sessions, we discussed about address bus, data bus, and control bus of the CPU, right? So if K is the number of address lines of the CPU, what is the maximum locations? 2 power K locations. So you can easily make one simple formula. Number of locations of the memory, let us say N, is always in powers of 2. K, where K is the number of address lines of the processor. Suppose the processor has 10 address lines, you can connect a memory of size 2 power 10, that is 1024 locations can be accessed. Suppose if K is 11, you can connect 2 power 11, which is 2048 locations, which we call it as 2K. So 1024 locations memory is called as 1K memory. 1K, uppercase K, which is 1 kilo. It's not 1000, please remember, it's a binary notation. Okay. Similarly, if K is equal to 20, is 1 M memory, 1 mega memory, 1 megabyte, because one location stores only 1 byte. So if I look at that, the number of locations N is 2 power K. So if I look at the size of the memory, let us say L or S, whatever, is N bytes. So you can write this equation easy to understand. Okay, I'm just writing here N bytes, where N is the total number of locations. That is also not arbitrary. That is decided based on the address bus size of the CPU. So 2 power K is the total number of locations in memory. One location stores 1 byte. So size of the memory or capacity of the memory is always N bytes. Okay. So capacity of the memory is measured in bytes. Okay. So this one you should remember correctly. Your mobile phone, for example, you have a RAM or a ROM. So you say 4G, 64G. So G stands for giga there, right? It's not 10 power 9, it is 2 power 30. Okay. So that way, so in your laptop, you have memory. So wherever you have memory, you are representing the capacity of the memory in terms of unit called as bytes. That is megabytes, kilobytes, gigabytes, something like that. Okay. And all the data in your memory is always stored sequentially in consecutive locations. And I said one location can store only 1 byte of data. But I also said that data can be 1 byte, 2 byte, 3 bytes, 4 bytes. Data can be big enough, right? So that means if I want to store a 32-bit data, let us say 32-bit data, which is a 4-byte data. Okay, then think of how many locations are required now. I said one location stores 1 byte. So naturally, 4 bytes means I need 4 locations. So if I start some addressing of the memory at say address 1000, so 1000, I'm just writing here, 1001, 1002, and 1003. These 4 together will store the same data. Please remember again, because total together is a 4-byte number, right? So the next number can be stored only at 1004. That is what is shown here, you can see. So if I assume 32-bit information to be stored in the memory, I need 4 locations to store each of that information. So the first address, if I start at some value, say 1000 or x or whatever, it will be x plus 4. Then next will be at x plus 8, something like that. This is what you are supposed to understand very carefully when you write assembly programs or anything later. This will be handy for you to understand the memory concept. Okay. So depending on the size of the data, number of locations required to store will vary. Okay. So for an image data, you need more. For voice data, you need much more. For video, you really need more than what is this required for voice also. Okay. This is how the memory structure and the storage of data looks like. Okay. Now coming to the next topic, how actually the assignment of this, that is storage, can be done. Okay. So we use one term called as byte addressability to define the storage. So each location of the memory contains 1 byte of information. This itself is called as byte addressability. That is, you are trying to access 1 byte at a time, or you are going to store 1 byte at a time. Of course, you want to store 2 bytes, you need 2 consecutive memory locations. If your information is 32 bits, then you need 4 consecutive locations. So just now I explained that. So there are 2 ways where you can, how you can store your data into memory. One is known as a big endian scheme. The other one is known as a little endian scheme. Little endian scheme is the one which is used in most of your desktop and laptops, because Intel processors use that architecture of little endian, whereas Motorola, PowerPC and all will use the big endian scheme. So what is that big endian and little endian? So we'll just try to see that now. So anyway, this is like a 4-mark question, explain big endian, little endian schemes with of memory assignment with an example something. So you can just look at this diagram and write few lines what I have written here. But to understand this, we'll just, I'll just highlight this. You can see I'm just highlighting this line. So what is the big endian assignment? The higher byte of data is stored at lower address and lower byte of data is stored at higher address. What is big endian? High byte of data is stored at lower address in the memory and low byte of data is stored at higher address. Just now I talked about data size, right? Once again, I'm writing, suppose 25, you write 25, you write is 1 byte, I said. Or suppose you write 3678, this is a 2 byte number. Suppose you write, say, 2675, 45, something like this. This is a 4 byte number, right? 2 digits is 1 byte, easy to at least recall and remember. Okay. So higher byte is what now in this is lower byte, right? This is the lowest byte. This is the higher byte. So in the big endian scheme, the higher byte of data is stored at lower address and lower byte of stored data is stored at higher address. What is that? I'll explain with an example again. In the little endian scheme, lower order bytes are in lower address only and higher order bytes are in higher bytes only. Clear? So this is the general schematic, but I think it's better to explain this example what I written here. So for example, let us say this is the data I want to store, 22, 35, say some number, any random number you can take, 50, 44, say 56. And this is the lower byte, lowest byte in fact, and this is the highest byte, right? So I have written this right to left now on pen and paper. We are used to like this. Same way, if you store in the memory, then it is big endian. Okay, so you can see 22 comes first, then 35 comes here. I'm just showing the arrow marks. You can see there. 44 comes here, and then 56 comes here, right? So the way you write on the pen, on the paper, if you store in the same way, then it is a big endian scheme. So higher byte is stored at lower address. Lower byte is stored at higher address. You can easily match this now, right? Same example, I will take the other side. So 22, 35, 44, 56. So just observe what I'm writing. Okay. Now what is this? If lower byte is stored at lower address, the reverse of this, that means you write in this way, but you store in the reverse way. You first store lower byte, then at the end you store higher byte. This is little endian scheme. Okay, lower byte stored first at lower address is little endian scheme. So all our desktop and laptop computers store the data in this way, because if it is using Intel processors, because that is the design of the architecture. So they have designed in that way, okay, to do that. Hope you got this point. So since it's a 32-bit data, definitely it takes 4 locations. You can see here 2000 to 2003. Next data will be from 2004 onwards, right? So this is how you try to understand what is little. This is just a 4 marks question, easy to answer in the exam without much worry. There is no equation to be derived or anything like that, okay? Then coming to the next small topic called as word alignment. Okay, so words are said to be aligned in memory if they begin at a byte address that is a multiple of the number of bytes in a word. Okay, so what do you mean by alignment? That means whether the data is stored at a particular address which can be a multiple of the byte numbers. Suppose you have a 16-bit information, that is a 2-byte information. So if the addresses are at 0 to 4, then it's aligned. Similarly, for 32-bit information, your addresses are at 0, at 4, at 8. This is what I have shown now. Something. So they are called as, they are said to be in aligned format. Okay. Now coming to the next small topic, memory operations. Now in the beginning when I talked about bus structure and memory, I said basically memory is of 2 types, read-write memory as well as read-only memory. That means you can read as well as write from the memory, write into the memory, right? So the only 2 operations naturally, because it's a storage device. So one operation is load or read or fetch, other operation is store. So I have shown you the simple diagram to understand that here. So you have an address bus of the CPU. This is what I said, K address bus, and you can have 2 power K locations here in the memory. So there is a set of 2 power K locations in the memory, and you want to read. So what you send the address first to the memory, then the processor will issue a read signal. That means it tells the memory that I want to read the data from so and so address. Then that data can be copied on the data bus and CPU can read it. This is the read operation. See, read and write, all these operations are always initialized with respect to processor, not with respect to memory. Read means processor is taking the data from the memory. Okay, that is, it goes to the processor register. Write means, or store means, whatever is already in the processor register is going to the memory location. Then also again you have to identify the address bus. So address first. So you read address bus for that. Then whatever the data in some register, say R1 or whatever it is going into the memory at that with the write signal. So the processor will issue a signal called as write, memory write. Then memory understands that the data is coming from the CPU. So that location, whatever is there, of course, in that location, if something is already there, it will be overwritten. Okay, the content would be lost, the previous content. It will overwrite on that existing data. Okay, this is how it is. So now we have come to end of this session. So there are some questions for you to answer and verify, especially with respect to overflow and all. Unless you practice these examples, you don't understand. So try to practice these examples and do it. And some definitions I have given. What is that and all? So for example, this is a simple question. A 32-bit word requires dash memory locations to store. So you can easily answer this 4 memory locations, because one memory location can store only 8-bit. Similarly, another one, in big endian assignment, lower addresses contain lower byte of data, true or false, I have asked. So it is just to recall all the topics, whatever we have covered in a nice way, so that you will be able to understand better. So in a big endian assignment, lower addresses contain lower byte of data is a false statement, because in little endian, this is true, right? So that way, the questions will help you to understand the concepts very clearly. Okay. So we'll try to end this session. I'll move on to the next session later. Thank you all.